Hi, I'm Kieran. I'm Vice President of Warwick Data Science Society. I'd like to thank you very, very much for coming to our Student Speaker Series. This is going to be a YouTube premiere, which means that if you have any questions, feel free to post them in the chat, and a number of people will be waiting around afterwards to answer your questions via text. So, as you might have gathered from the title, this is going to be a Student Speaker Series. We're going to have a number of student speakers. The first is going to be Tim Hargreaves, who is our president, but he's also been a data scientist at AstraZeneca for over a year now. He's going to be talking about how applications of thermal and material physics can be used to solve Sudoku problems. Afterwards, we're going to have Fernando. He's going to talk about various forecasting models that can be used to predict the outcomes of US presidential elections and also elections around the world. And finally, we're going to have Martin, who will be discussing automatic differentiation, which is a way of optimizing mathematical functions without getting into the nitty-gritty detail of those functions. So again, thank you very much for coming, and if you have any questions, post them in the chat section of this YouTube premiere. Thank you.
Hi there everyone, I'm Tim and welcome to this talk, Solving a Sudoku with Physics. So as already mentioned, we pre-recorded these talks, all the talks in this event, just to make sure there's no chance of any technical difficulties, but all the speakers in this event will be watching the live chat. If you have any questions, please pop them there and we'll answer as soon as possible. If you watch the event later and the live chat is no longer available, please pop them in the comments and we'll get back to you there. Okay, so I want to start this talk by asking a motivating question. Can we solve a Sudoku by randomly guessing numbers? And if you think about this problem for a second, you should come to the conclusion, yes, you can. And the reason for this is that there's a finite number of possible Sudoku boards. So the number is massive, it's more than the number of grains of sand on the Earth, but it's a finite number. We could simply run through all these and check, do they line up with the numbers we've been given? And if so, we found a solution. Now, you could be clever, you could try and reduce this number down by noting you can rotate a Sudoku, you can reflect it, and it's still really the same puzzle, and get this number down to something a bit smaller. Still a massive number. And you may be thinking of all the clever optimizations you could do. You could, reduce this, that, and the other, use this clever symmetry. But still, it's going to be a lot of numbers. And in the long run, any sort of brute force approach like this, randomly trying things, and just seeing what works, is going to be really difficult to do and take a long time. So really, we need to reword our question and reframe it as, can we solve a Sudoku by randomly guessing numbers in an efficient way? And surprisingly, the answer is still yes, we can, depending on exactly how you define the word efficient, but we'll get to that later. And that is the topic for this talk, an algorithm called simulated annealing, inspired by physics and material science, that is essentially just random guessing, but in a very clever way that allows it to solve problems like Sudokus in an efficient manner. And so I've split this talk up into 4 sections. We're first going to have a brief exploration of what nature does for optimization, the ideas that nature presents us related to optimization. We'll then talk about a specific example, simulated annealing, and then in the third part we'll apply that to solving a Sudoku. With the code provided and seeing the results of that. And then finally, we'll talk about the other applications of simulated annealing and some further reading you can look at if you want to learn more. Okay, so we're going to start off by looking at some examples of how nature is really, really good at optimization. And the first lesson we're going to learn about is soap. So we have a question here. What is the cheapest way to connect 4 villages located on the corners of a unit square, so a square with side lengths of 1. And when we mean cheapest, we mean the least amount of road used. And if 2 roads overlap, well then cars can jump from one road to the other and kind of travel across those. So let's start with a very simple solution. It's not the best one, but it certainly works. So we just draw a square, total length of 4, all the villages are definitely connected here. But this is far from maximally efficient. For example, we could remove one of these sides. Now, the villagers that have relatives in village B and live in village A, they're going to be annoyed by this solution. It's a long way around, but we only care about making the cheapest solution, and this is certainly cheaper. There are only 3 units of road here. We can do even better. We could perhaps make a cross. And so we now just have these 2 square root of 2 side lengths, if you know Pythagoras' theorem, and you can cross over in the middle to get from A to any of the others and vice versa. And the total length of this is about 2.83, so slightly better than the 3 we had before. And when I first saw this problem, this is the solution that I came to, and I was convinced it was correct. How could you possibly do better than that? And it turns out you can. And a way you can find this solution is using soap. So what you do, you take 2 panes of glass, and between them you put 4 kind of metal poles on the 4 corners of this square. Then you take this container and you submerge it into soapy water. And then the soap will form a film giving the optimum solution. And it'll look something like this. So on the left here we have those 4 poles connected between glass. And then you probably can't see it on the video, might be a bit tough. There's these the soap film here forming a pattern that looks like this on the right here. It turns out that this is the optimum solution. It's got a length of 2.73, which is about 0.1 better than the 2.83 we had before. And the solution is actually parts of hexagons, which is a shape, and we see it in honeycomb. It's a really good shape for efficiency in nature. But the interesting part of this is how the soap found the optimum solution. And the answer is the soap is trying to minimize the amount of energy it has to expend in having its structure. And energy is proportional to the amount of surface area. And so by trying to minimize its surface area, it also minimizes the amount of distance or the amount of total road used in this solution. And there's many other examples of how soap can solve similar problems like this. It's just one of the many examples of how nature is really attuned to optimization. And so another brief example is evolution. How can we train a bipedal, so a 2-legged robot, to walk? Trying to program this in manually is going to be a really difficult task. There's a lot of complicated operations going on there. Instead, what we can do is just start with a pretty much random solution in the first generation, have loads of different variants of that, see which ones do the best, breed those, combine them together, and repeat this process. It's evolution. If you do something like this, I won't go into the details, you'll end up with some really strong walkers that have learned over time, just by natural selection, what the best responses are given its current state. And so there are many, many other examples. I might throw one in the chat as we're watching live of how nature can be used for optimization. But we're going to focus on a specific example called annealing. Okay, and we're going to take this annealing method and try to turn it into an algorithm that we can use for solving problems, and that's known as simulated annealing. But let's start with the real deal. What is annealing? So annealing is a treatment used in material science to try and improve the structure of a material, commonly a metal. So metals are made of these crystalline structures, and sometimes the atoms can get out of place, and that causes a lack of robustness and strength in that material. And so what we can do, we can heat up the material, giving their atoms more energy, and above a certain temperature, they will begin to, they'll lose the crystalline structure and be allowed to move freely around the metal. And then as we slowly cool down the metal, the atoms will slot into better positions in the crystal lattice than they were before, ending up with a much more crystalline structure in the end. An example of this is in the bottom here. So this is just a standard material that's been just no heat treatment, and then 2 other ones have been heated to 550 and 650 degrees Celsius. And we see that the one on the right has a much more crystalline and ordered structure, as the atoms were able to move around and as they cool, slot down into the correct positions. And so what we want to do is take this physical process and try and turn it into an algorithm. And so what we're going to do, we're going to start with just a random solution to our problem. That's kind of the same as starting with just a random arrangement of atoms in a metal. And we're going to start with a hot temperature. And temperature is just going to be a property of our system that's going to decrease exponentially with time. So basically we're cooling the system down as we go. And then what we're going to do, we're going to make small changes to the solution, similar to those atoms moving around. And then we're going to randomly accept whether we want those changes based on the temperature and the amount of improvement that those changes made. So if the improvement to our solution is big, then we are more likely to keep it. If the temperature is high, we're more likely to keep it. So basically, lots of changes at the start, and as we cool, things start to slot into place just like those atoms, and and we kind of approach the more optimal solution. And as I mentioned before, we reduce the temperature with time, often in this exponential fashion. Okay, and this kind of nature of just randomly starting with something, randomly making changes, and then kind of slowly approaching the optimum has given stimulated annealing, it can be referred to as just blind luck on steroids, because the process is entirely random. There's no kind of knowledge of the system, it's just randomly trying things. But through this cooling process, it actually ends up being pretty powerful and efficient. And so I'm going to start with a very kind of rough hand-wavy example before moving on to the more complicated Sudoku example. And that's going to be trying to find the minimum of this function. So you can imagine we have some sort of dial on a computer or system or a machine, and we have to turn that, and as we turn it, the cost of producing whatever we're producing will change in this very complicated fashion. And we want to minimize this, find what dial position will give us the lowest cost. And we can solve this using stimulated annealing. So we start with a completely random point, just initial random state, and we start there. And we start with the temperature being really high. We then randomly choose another point by taking the original one and just modifying it slightly. And because here the temperature is still fairly high and we had good improvement, we're going to accept this point. We're now going to iterate again. So we're going to take our new point here, we're going to add some random noise to it, and we end up here. And again, we've improved, the temperature's still fairly high, so we're going to keep this one, or with high probability at least. We then add this point. So we took our last one, moved it a bit, ended up here. So now, the temperature's pretty low, we didn't improve, we got worse. So it's likely, probabilistically, we're going to reject this point and not include it in our annealing process. So we reject that, it's not included. And so now we're still on this point at the bottom here, we add some random noise. Now the random noise goes in the downwards direction, or it makes our function minimize further. The temperature is quite low, so we're unlikely to accept things, but because we did have an improvement, that helps the probability, and we end up accepting this. And so we just keep doing this, a few more times, and that's going to gradually approach this minimum here. And you can see the beauty of stimulated annealing in that we were going towards this local minimum, it's a good solution, but not the best. But because the temperature was still high, we were allowed to move around and jump around as we are getting started. And then as we cool, we start to approach this global optimum solution. So that's a general idea. A bit hand wavy, it's not exactly what's happening, but it's a good intuition. Okay, so how can we take that and apply it to a Sudoku problem? So first we're going to have to define what our initial random state looks like. And so we're going to do this by taking all of the fixed values, the values we're given in the Sudoku, and then for each 3x3 square inside of the Sudoku, we'll randomly fill that with the remaining numbers. So here we started with 6, 3, 8, and 2. And so now we'll take the other remaining numbers that don't appear there and just randomly place them in each cell. And we do that for each of these 9 blocks of 3x3. And then the small changes that we're going to make, the atoms moving around while they're hot, we're going to randomly pick a square out of the 9 and then take 2 non-fixed cells in that and then just swap them around. So we might pick the one in the top right corner and then pick these bottom 2 here, the 9 and 7, and we just swap those around. And we keep repeating this, and then we accept the change based on a probability related to the temperature and how much of an improvement we made to our solution. So that's the next point. How do we measure if our solution has improved by making a change? And we're going to do this by counting the number of mistakes in each row and each column and adding these all together. And we're going to refer to that as the total cost of a solution. And so, for example, if we had this column here, the reds are the fixed numbers and the yellows are the ones we randomly put in. We see that we had 3 1s, therefore there's 2 mistakes there. We only want 1 1. And there are 2 3s, so there's 1 mistake for that as well. So in total, this column has 3 mistakes. We'd add those up for every column, for every row, and that's our total cost. And so a perfect solution, a correct solution, would have a cost of 0. That's the target here. Okay, and finally, we have to define the details of the temperature, what our starting temperature is, how fast we're going to cool down, and how many iterations we have for each temperature. We're not going to get into the details of how we decide these. They're included in the code, so we're not going to worry about those for now because they're non-essential. Essentially, you can choose any values here, but certain values are more likely to give you better results and faster conversions to the solution. Okay, so let's see this in action. If you follow this link here, you'll end up on this page here. And there'll be a link to the talk here and a link to open this notebook here, which has the code in. You can run it on Google Colab without having to install Python. Just have a go yourself, put in your own Sudoku if you'd like. So I'm not going to go through all the code. You can have a look yourself. If there's any questions, please get in touch. Be happy to answer. But the idea is we start with a Sudoku. So something like this, using underscores here for any blank values. And so this is our initial Sudoku here. And we're going to start by randomly filling, defining a random state, a random initial state by taking every 3x3 grid, putting in the random missing values. And so look something like this. The green are the ones we were given, and the reds are any mistakes. So lots of mistakes to start off with. Hopefully with time and with the annealing process, we will reduce these. So we go through the rest of the code here, and the final block of code is this simulate here. And this is going to do the solving. And so pay attention here, because it's going to go very quickly. It's a very good and efficient algorithm. I'm going to run this, and it's going to start solving. The cost is reducing, temperature is reducing, and then, oh no, okay, it seemed to get stuck for a second there. Let's see how it's doing. So cost is reducing, and then there we go, solved it. So you notice there that it was going towards a local minimum, and then realized, actually, I can't find a solution here. But because the temperature was still fairly high, it jumped back up and started going down to another solution, and then found the actual solution in, what was that, a few seconds? So it's really quite an impressive algorithm. And you can try this with any Sudoku that has a solution, and it should do just fine. Okay, so a few comments on that. That is far faster than a brute force, just randomly choosing without annealing could possibly do. It's still not perfect. There are improvements that could be made to my code to make it faster. And there are also more optimized methods for solving Sudokus. You can use constrained optimization, backtracking, or a combination of those two, and that would do much better. But the important thing is, this method is simple to explain conceptually. You don't require any strong mathematical understanding. It's just a generic physical algorithm, and it's really general. Like, I could apply this to many different types of problems, and it would work the same, whereas these optimization and backtracking are specific to Sudoku. Okay, so what's the next steps? What's the other applications of this algorithm, and how can you learn more about it? So here are a few other applications. If anyone has a go at actually applying simulated annealing to these problems, please let me know. I'd love to see the solutions. A Rubik's Cube you could solve using simulated annealing. Scheduling problems, so trying to figure out how to fit a load of tasks that have certain orders, or do timetabling between classes. Simulated annealing would do a great job at that. The traveling salesman problem, if you're familiar with that, the shortest path between a load of towns. Or just, as we saw earlier, minimizing a function, trying to find the bottom of a function. And really, simulated annealing can solve any form of combinatorial optimization problem. So anything where we're having to make choices and there's an associated cost associated with each choice. So it's really a very general algorithm that's very powerful. Okay, so I will close off with some further reading you can look at. First is an example of solving the traveling salesman problem using simulated annealing in R with a shiny dashboard to accompany it. There is a package for simulated annealing in Python. I implemented it manually, but if you want a package to get you kickstarted, you can have a look there. And there's also a very good research paper, simulated annealing, which gives the algorithmic details. I think it's in C++ of simulated annealing. If you want to learn more about Sudoku solving itself without simulated annealing, there is a blog post, a research paper, Sudoku as a constraint problem, that kind of talks how you can view Sudoku as a constrained optimization problem. And finally, Donald Knuth and the art of computer programming talks about this backtracking algorithm that can also solve it. So with that, thank you everyone for listening. I hope you've learned something new and are interested in maybe having a go at applying simulated annealing to your own problems. So with that, I'll pass over to Fernando.
Hi, I'm Fernando, and I'm going to be talking to you about forecasting the presidential election in the United States. I want to start by thanking Tim and all the WDSS team for the invitation. I'm really happy to be here, and let's get going. So you've probably heard that Biden is beating Donald Trump right now. But we all remember that 4 years ago, the same was said about Hillary Clinton beating Trump, and it didn't happen. So how likely is it that this time Trump will lose? We're going to talk about it, and we're going to talk about the general task of forecasting elections, which I think is interesting for a lot of several actors, including, of course, your too frequent Twitter fighters. But I think it's a difficult task sometimes. It's not easy because you have relatively short history. There are not high frequency of elections. And there are different political systems. It's not the same to forecast a US presidential election, and it would be to have a forecast for a UK parliament or my own home country's presidential election in Mexico. But also importantly, as data scientists, we have to always acknowledge and remember that there are a lot of different data sources, and with that there comes a lot of different qualities. And if you don't remember that or acknowledge it, you will have surprises, and not nice ones, down the road. So let's talk about two big kinds of forecasts. You have heuristics and rules of thumbs, a lot of pundits, and you'll hear about that a lot. And you have statistical models. No surprises here. We like statistical ones, right? It's not only because we like modeling or because we think modeling is beautiful or statistics are beautiful. And it is because, yes, forecasting who's going to win matters, and heuristics and rules of thumb actually point towards that. But we also care a lot about how likely that is. We want to manage uncertainty, as Warwick's department says. And in order to do so, we understand probability as a measure of uncertainty. Not only as a measure, but a quantifiable measure of uncertainty. And within the Bayesian framework, what we usually do is we propose a data generating model, how our data will come about. And we include parameters, latent variables, a lot of different statistical constructs that allows us to propose this history. And then we usually, in practice, end up applying Bayes' theorem, which has a really nice interpretation. We start with some prior assessment of our uncertainties upon the unknowns that we're interested in. And we want to reduce that uncertainty by gathering information in the form of data and proposing its own model, right? So this is our prior distribution, probability distribution, and our likelihood of data given the parameters or the unknowns. And what we're going to do is, using Bayes' theorem, we update or reassess this prior uncertainty through the data we observe and end up with a posterior probability distribution of our unknowns given the data that we actually observed. So conditional on what we observed, how about our hypotheses? How likely our hypotheses are? And so let's start with this. First, the fundamentals, that prior. It's the economy, stupid. Heuristics, rules of thumbs, everything points out to the fact that there may be some structural or fundamental factors that allow people to predict reasonably well in advance the result of an election. And as an example, you can do that mathematically or probabilistically, statistically, with different models, like Abramovitz's time for change model, which is based on three basic ideas. There's a bad economy, it's time for change. There's a bad incumbent, it's time for change. There's been the same party governing for a long time, it's time for change. And there's some empirical evidence that suggests that we can do that. So there's a lot of things going on that could allow you to make a good prior probabilistic forecast and deploy a lot of different tools, not only regression, but also to avoid the important problem of overfitting given the small quantity of data, you could use elastic net regularization, leave one out, cross-validation. You could be more heuristical if you actually think that there's more uncertainty, for example, this year given the pandemic, and include a little bit more components into the mix. This is an important and non-trivial task that will require a lot of domain knowledge, but it's just the starting point. It's important to keep in mind, and the idea is make a good prior probabilistic forecast of what you think is going to happen. But then you want to know the answer of a question, ask people that are in charge with that. So let's take polls. Electoral surveys are our main source of information when it comes to knowing or inferring things about the state and evolution of a political campaign. And they are so because they are based on the notion of random sampling. Probabilistic polling is one of the key tools that we could have. And the most basic model that we can propose, and it's not only the design of the survey, but as a model, a statistical one, it's the binomial, which is just based on the idea of independent Bernoulli trials giving a shared probability. In this case, this shared probability is of voting for a particular candidate, which, just for the sake of argument, let's say it's Biden. And we have, an amount of respondents, and Y of those say they actually prefer Biden or will vote for Biden. And the probability of someone answering Biden will depend on a latent preference in the population. And this also points to another fact, and that's the notion of snapshots. Polling indirectly is based on the idea that the population parameter of interest, it's the result of a hypothetical election held at the time of the survey. It's not a forecast per se on what's going to happen the day of the election, but what are the preferences when the survey was conducted. And given this, what we would like to do is not only take one poll, but aggregate more than one throughout the campaign. So let's do a poll of polls, right? We will have K polls during the campaign, and that will allow us to model latent preferences as evolving in time from the start of our analysis towards the end of the campaign and election day. So now we index the same model as before, but index every poll and refer to it as the time when it was conducted, right? But don't forget about total survey error. Our binomial likelihood is only addressing sampling error, the fact that we are not making a census of the population, but we are taking a sample. That's important to recognize, but there are a lot of different elements that go into possible biases and errors in our survey statistics. And importantly, we can think of some of them as house effects. Even when one polling organization is trying to do everything by the book and methodologically sound, there are a lot of different steps in the way that require decisions. Are you conducting a poll asking for a question worded this way or the other? Like question wording, it's important. Are you conducted face-to-face surveys? Your interviewers, how qualified are they? How trained are your interviewers? How do you process the data? Are you using Mr. P? Are you only using racking? Those kind of decisions could have a bigger impact down the road and add error from just only the sampling one. So we can think of those as house effects, because even though they exist, it will probably be variance between polling organizations, but one single organization will probably have the same decision process throughout the course of the campaign. So we can think of them as house effects that are constant during the campaign, but vary across polling organizations. And what we do is we transform our simple binomial model into a generalized linear model that will allow us to decompose our parameter of interests into signal and noise. So we still think of survey estimates as measurements instruments of latent preferences, But now these latent preferences, the true ones, are being disturbed both by non-sampling error attributed to house effects and the sampling error attributed to the fact that we are conducting a sample or a poll. But of course, this schematic tells us there are a lot of different sources of error, so we could decompose these a little bit more and acknowledge explicitly the fact that there could be differences between registered and likely voters polls, between face-to-face or telephone-based surveys. We could include corrections for partisan non-response bias and different things that will still have the same idea. It's the latent preferences that being disturbed both by the sampling but also by non-sampling errors that could be decoupled but could be thought of as these delta K parameters, right? And now we go to the question of how things evolve during the campaign. And it's back to the future. Let me try to explain what I mean by this. Remember our fundamental forecasts? That was our prior guess on how things will go on election day. And our poll of polls is telling us how things are going, how things are being observed at each point in time. So what if we travel backwards from election day, what we think is going to happen in the future, and back into what we are seeing in the polling? And what we do is that we start with our prior forecast and we relate that to the latent preferences at the time of the election. And at each point in time, here on the blue font, we condition on the next period of time. So where are we going to be? We know that. And the future, we are assuming that we have a guess. And where are we at the moment? This way we are traveling backwards until the first day of the analysis. And we are doing this in a random walk behavior, in a backwards random walk behavior, which this means that there's another parameter, sigma squared, that's going to tell us how things change between periods, how much there's change there is. And of course, as election day approaches, this backwards random walk has less time to adapt to our fundamental forecast. It's like we're trying to breach our prior guess with the tendency that's being reflected in the polls. When we only have few polls and there's a lot of time between the last poll and the election, there's a lot of time for this drift to eventually converge to our prior forecast. So the forecast will have a lot of impact. But once the tendency starts being clear and there's less time, so as election day approaches, then the polls are going to dominate the forecast and our prior will not have as much of an effect. And that's it. That's basically it. Well, actually not, but that's the general idea. And at this point, it's important to talk about, okay, but what about 2016's? And pardon pun, the logistics were off in 2016. Well, let's take a closer look. First, the actual result of popular vote was Clinton 48.2. And for example, Nate Silver's 538 model, his last prediction was 48.5, which is pretty good, pretty close. But the thing here is that popular vote is not the rule of the game. We should model electoral votes, not popular votes. Each state has a fixed number of votes that go into the winner, so the winner takes it all. And that's important. But the second thing I want to note is, okay, Nate Silver did that and still gave Hillary Clinton a 71% chance and Trump a 27% chance. Let's think about what 27% means. Furthermore, what does 25% probability events means? Those are usually talked about in terms of 1 in 4, right? It's not that uncommon for a 1 in 4 event to actually happen. NFL kickers could miss field goals from 40 to 45 yards, and their actual probability is more or less 25% of missing the field goal at this distance. Or if you like or have played the game of Risk, you know it's not the rule that one die will beat the 2 defender dies, but it's not unheard of that you take 1 unit away. So why are we surprised that Trump won if he had that amount of probability to do so? Well, one thing is that this was probably the most bullish model on Trump. A lot of other models, they said Hillary was absolutely going to win. 95% chances, 99% chances. And the reason why there was such error in that assessment of probability is probably because of correlation. What happened with polling in 2016 was small but correlated errors in particularly battleground key states in the Rust Belt and in the Midwestern. So the idea here is that, Pennsylvania is probably more similar in its political developments to other states close here than to California or Texas, or even some non-geographically related states like Florida. And similarly, South Dakota is way more similar to the neighboring states than to Georgia, Deep South, or Texas. So you should explicitly model that. And here we have two lessons from our previous simplified version of the model. We have to model states and we have to model them correlatedly. So what we are going to change is that our latent preferences now are 50 preferences, each one for each state, that are still going to evolve through time. And we will still allow for temporal national shocks. But the thing here is that now we need state level polls. We are still going to use national polls. I'm not going to go into the detail of how to do that, but it's possible. But now we have to have a really important element that are state level polls, which are usually of lesser quality than national polls. And that's one of the biggest lessons from 2016. You've got to have good state level polling. And of course, our placeholder for non-sampling error. But now in our Back to the Future, in our random walk, we have vectors. And now that means that we model them not by a univariate normal, but by a multivariate normal. And that has a covariance matrix parameter where we can model explicitly the correlations between states. And here we have to put a lot of attention and a lot of detail in our modeling. But the idea remains the same. Fundamental forecast is our prior, and we go back in time using the correlations. And the correlation in states also helps to fill the polling gaps. When you have one state that hasn't been polled in a while, you can borrow information from neighboring or similarly correlated states. And that's a shared information that one could have. Of course, there are some technicalities given the model we have been presenting here, like you have to have a constraint here for the model to be actually estimatable. But we're not going to concentrate on that. The bottom fact is that what we have is latent preferences at election day. And we translate those into vote shares for candidates in each state. And the winner takes it all. The winning candidate in each state gets assigned its electoral votes with terms and conditions in Maine and Nebraska. But then if it's so simple, why all the fuss? It means that we have now a probability model from which we could simulate from. And we have a lot of different possible trajectories that are plausible with our modeling assumptions and the data we are observing. So that gives us a lot of different simulated elections and winners. We translate our prior forecast fundamentals and our polling observed data into votes and simulated elections that gives us who is going to win the election and arrive at a final probability. How likely is it? And these are the economists on the left and 538's model on the right, probabilities for the election. So Biden is actually being a bigger favorite than Clinton 4 years ago. So we could hope that this actually happens for the sake of the polling and the forecasting industries. But keep in mind that there are a lot of red dots or squares here. It's not out of the blue that Trump could win. So with this, I hope that you've enjoyed and kind of gotten a better feeling of how forecast models are constructed, and happy to answer all your questions. Thank you very much.
Hello, my name is Martin Smith. I'm a third year Morse student here at the University of Warwick, and today I'm going to be talking about democratizing differentiation, which will hopefully be an introduction to automatic differentiation, how it works, and how it's applied in the real world. So, why democratizing differentiation? Well, I just want to show you that it can be easier than you think. There are 3 different ways I'm going to talk about, and one of them, the last one, automatic differentiation, I think is pretty cool. And it's actually pretty easy to understand if you can get the building blocks, which is what we're going to go through now. So, let's say you're at a birthday party, your own birthday party, but it's a nightmare situation. All of the people you invited, they didn't turn up. Oh no, you've got to eat a chocolate cake all by yourself. Oh no. Anyway, we all know that eating too much chocolate cake, while fun for some amount of time, eventually comes back to haunt you when you start feeling bad later. Too much sugar, right? Too much fat, all those things. Not good for you. Put on the weight. Nah. So, we want to eat as much chocolate cake as possible without getting sick. Essentially, we want to make ourselves as happy as possible using only this chocolate cake. Now that's a challenge that I don't think I'm qualified to talk about, but good thing is we can model this using a little graph that we've got here on the right. So here the graph is. In the y-axis, we have happiness. We want to maximize this as much as possible. And on the right, on the bottom, we have percentage of cake. I can't spell cake. Cake eaten. And then, by me. Because obviously if this doesn't apply. Anyone can eat 100% of the cake if we all share the cake. But if I am the only one who's eating the cake, that's not great. So we can see here that if we want to maximize happiness, where do we go? Well, we kind of look for the highest point. What's the highest point? It's roughly around here. It looks to be around, let's say, 60% of the way there. So if I eat a half and then another tenth, I'm happy. I'm as happy as I can be. In fact, I know I'm as happy as I can be because if I eat any more, I'll go down slightly. And if I eat any less, I'll also go down slightly. So how do we know we're at the top? How do we know we've maximized our happiness using this cake? Well, the function has stopped. The function where we're at is completely flat. Now that is pretty obvious if you've done any sort of, maximization, any of those things. It's pretty obvious, right? So this is just sort of the motivation of why we want to differentiate things, because it's really useful. Maximization, optimization, machine learning. Some keywords there, got some buzzwords. Any of you corporate guys out there, sure you're having a great time. So, what's the first way that you might think about when you're trying to differentiate something? It's probably the way you were taught, which is called symbolic differentiation, where you take the symbols, you manipulate the symbols until you have the derivative. So let's do it here. Let's do a really quick one. 4x squared, take the 2, put it at the front, multiply by the 4, x, 2 minus 1, that becomes just 1, which we can get rid of. And then we have the plus 2x, which differentiates to plus 2. Now this is pretty good. Let's put an equals there. It's pretty good because, 1, it's exact, and 2, well, we can use any x though. We can use any x possible. We can put minus 2.4. And it works. It's great. You can put pi, you can put tau. The point is you can put any x, right? We didn't just discover it for one x, we've discovered it for any x. And it was pretty fast. It was kind of fast. It wasn't the fastest thing ever. I don't know about you, but I've done differentiation faster than just now. I was trying to explain it for the slow ones, But the problem is, we can make really, really, really long expressions by differentiating them like this. And everyone, just hold your breath for a second. I'm about to scroll left. And this is a dangerous thing to do. But, okay. Hopefully you're all still here. Because you just noticed that I uncovered a function and its derivative. And the derivative is going to grow exponentially long the more times we differentiate it. That's terrible. We can't have that. Our computers can't have that. What if we try and put this into a computer and differentiate it 5 times? That's not possible. The computer will go, no thanks. I don't have enough RAM for that. I don't have enough memory. I can't even remember the function you put in the first place because I'm trying to calculate the 5th derivative. No. In fact, if I ever give this talk live, I hope that there's a audible shock among the audience when I try and suggest that we even bother differentiating this. It's not good enough. It's not possible. We have a problem. Symbolic differentiation has a problem. In fact, it has two problems. We've doubled the number of problems. How do we do that? Well, we just realized that we can't use if and else statements in these functions. How do you differentiate if? How do you differentiate if? No one knows. Well, computers do. I do. But symbolic people who live in the symbol land, it's all these people here. They're out of luck. They can't do much. It's a pretty good drawing. I'm pretty proud of that one. Anyway, so you're scrambling to think, how do I differentiate this kind of function? Or just, can we solve the first problem? Can we differentiate things faster than we already have? Good thing is, you made a friend when you were at university. In fact, you've made two. I'll come on to the second one later, but you've made at least one friend. Unfortunately, this friend is an engineer, so we can talk about talking to engineers later. But so here's your engineer friend. What a good-looking guy. There he is, really happy, looking at the ground there. And he says, well, why don't we try and calculate the derivative of this function using the limit definition? And the limit definition is basically illustrated by saying, if you want to calculate the derivative of a function, you take 2 points. If you want to calculate it at this point, you slowly move this point closer and closer and closer, and each time you draw a line between them, and hopefully you get close enough that this line approaches the tangent. Well, I mean, it does approach the tangent, but hopefully it gets close enough that you can approximate the tangent reasonably well. And you can see here, if you put the dots right on top of each other, you do actually get the tangent. But unfortunately, computers don't really like right on top of each other. Because what does that mean? Well, this becomes 0 over 0, and that does not make computers happy. In fact, here's a computer, and here is it being really unhappy that you've done that. Please don't ever do that. Try doing that on a calculator. It'll probably give you a sad face. And if it's been programmed by a nerd, probably give you something like undefined, or you can't do that. This is illegal. Illegal maths. We don't do illegal maths here. Completely legal. So, what's the problem? The problem is we'll always have some sort of error. We'll always have, h will be 0.00005. It's too big. It's too big. Sorry. We need a exact derivative here. This is the maths realm. But then you also have the problem that if you're dealing with really small numbers, your computer can't even handle that. It can't handle numbers that are so small. So maybe we're getting closer and closer and closer and closer, but unfortunately these numbers are getting smaller and smaller and smaller, and at some point the computer just says, it's 0. The number is 0. This number is just 0. You're trying to divide by 0. We're back to this problem again. We can't have that. Okay, thanks engineering friend. Maybe it works for you, doesn't work for us here in the computer science / mathematics / data science realm. Got to cover all the bases, I don't know who's watching. But there is something better. I'm here with the solution. I have all of the solutions. Well, I have a solution. 2 of them, in fact, because what we're going to discuss, you can actually do it in 2 ways. What's the solution? Well, I'm glad you asked. I'm sure you did ask. Everyone asks. I'm a very interesting person. So here comes our computer science friend, and he says, let's build a tree. Okay, computer science friend, how about you go back indoors? This guy hasn't come out of his room in 20 years. He doesn't even know what a tree looks like, and you'll see that later. Well, in fact, let's just show you what he thinks a tree looks like. So here we have a really scary function, which I'll go over in a second. And this is what he thinks a tree looks like. Now, I don't know you, and you don't know me, but we both know what trees look like. I'm looking out the window. I'm seeing, there's green, okay? There's some green, there's some brown. I'm not seeing none of them leaves. I'm not seeing a trunk. I'm not seeing, there's normally some squirrels. Yeah, you're right, mate. There's some squirrels, acorns, I'm not seeing none of that here. We should just call it a tree, all right? We just call it a tree, move on. So, what's at the root of this tree? It's the inputs of the function. Except we've given them funny names. Now, instead of calling them x1 and x2, we call them w1 and w2. Great. Thanks, Martin. What does that let us do? Well, kind of nothing. It's just so we don't forget that we're working with derivatives here. So, what we do is we take this function, which, notice, it's a function of 2 outputs, because there's a comma here. And after we break this function down into its constituent parts, and then we teach the computer how to derive or how to differentiate these constituent parts. And so you can see here that what we've done is we've taken this plus, we've said, well, the plus has an x1 and an x2, which we're now calling w1 and w2, and we put them both onto the plus node. Great. Then we have this is a multiplication, so we have a multiplication here, and this looks like it should be the multiplication point. So we take w1, w2, and we multiply them together. And then we have a sign. So we take this new thing that we just calculated, which we called w3, and we put it in a sign. So we call w4 sine of w3. This is a w and that's a 3. Cool. And you can see that that's all been represented in this lovely tree. And finally, to calculate the first part, we just take we just take w4 and add it to w5, which we already calculated, and then if we want to get f, we take these two parts and we have f, because of this one here is just the multiplication of the first two. So pretty cool, huh? We made a tree. Now, I don't know about you, but trees normally take longer than that to grow in real life. Turns out this is pretty fast. So what happens now? So what automatic differentiation does is it takes advantage of the chain rule. Now, what's the chain rule? Well, we all learned that when we were younger. dy dx equals dy du times du dx. And basically what this is saying is if you want to differentiate a function with respect to a variable, you can first differentiate it with respect to another variable, and then just differentiate this other variable with respect to the original variable. Multiply it together, and you're all fine. So that's what we do. So what happens is, if we're doing the forward mode of automatic differentiation, we start at one of the inputs, and we see what journey it makes through the function. And as we're doing this, we differentiate along the paths. So here we have w1. What's the derivative of w1? Well, w1 is x1, and we're differentiating with respect to x1, so that'll just be 1. Derivative of w3, well, that's going to be w1 plus w2. w2 differentiation with respect to x1 is 0. w3, so that'll be w1 plus w3. There's a reason we give this to computers, right? But the point is, as we go along the tree, we take derivatives based on what was before. And eventually what happens is you can just, you give it a point. So you give a function a point. You say we're going to take f at 2, 3. What is the derivative at 2, 3? Okay, important thing to note here. Automatic differentiation does not give you the analytic expression of the derivative. It can only give you numbers. If you try and input, well, actually no, you can't. You can't try and input an x or a y. You can only input numbers. The good thing is, after you've made this this tree here, you can just use this tree for any combination of numbers that you want. So if we try, let's see what's next actually, I've kind of forgotten. Okay, so let's look at forwards mode and backwards mode and compare them to each other. So what did I say forwards mode was? Forwards mode is you start at one of the inputs and then you follow it along and you see how it affects each output. So you can see here that W1 would go along here, and then all the way along here, and it would affect the first, because this is meant for the first one. And then it would also go along here, and go along here. Oh, and it would also go along here as well. So it would affect the first one, the first output in 2 ways, and it would affect the second output only in 1 way. So what this is saying is, if we change W1, we also change both parts of the output. And how much? Well, that's determined by the tree itself. Wow, what a cool tree. What a cool way of doing it. So all we've done is we've deconstructed the function into a tree, differentiated it along this tree, and then seen how what happens when we change one of the input variables. So we follow along the tree and we see what happens when we change the input in the output. So what happens when we maybe add a little epsilon to x1? What happens in the output, the first output? Okay, this. And what happens in the second output? This. Unfortunately, this isn't very good when you have a lot of inputs to check, because you can only check them one at a time. So another way you can do this is you can scroll down quickly. You can construct the tree when you go forwards, and then you actually differentiate backwards along the tree, and you can see which inputs affect each output. So we can see here, if we start from this output here, this is supposed to be coming down here, we can say, well, if we start here and we change the output a bit, in order to get this desired change, we'll need to do a change to x1 and a change to x2. And if you've ever heard of neural networks and you sort of know a little bit of what's going on with neural networks and backpropagation, this might start ringing some bells to you. But hold that thought for a second. So to sum up, automatic differentiation: you construct a tree, you teach a computer how to do very basic derivative arithmetic. What happens if I differentiate a plus? What happens if I differentiate, maybe the product rule, the division rule, sine, cosine, all things like that. And then you also teach it the chain rule. And then what happens is you can automatically go along a tree and differentiate along the tree. So by the time you get to the end, you can see what happens when you differentiate in a certain direction. And if you're a math student, basically what happens is when you do one iteration of automatic differentiation, forwards mode, you get one column of the Jacobian matrix. And if you do backwards mode, you get one row of the Jacobian matrix. Okay, but if you don't do math, don't worry about that. It's just something for the maths people to know what's going on here. So backwards mode, you might be thinking, well, okay, when do we use backwards mode? When do we use forwards mode? And if you're a mathematician, you might already have sort of taken the hint from when I described the Jacobian. You use forward mode when you have a few inputs and a lot of outputs, because you can see you only run the function once or twice, once for each input, and you can see everywhere that this input affects each output. And the opposite is true for reverse mode differentiation, where you take every output, you wiggle it around a little bit, and you see where does this wiggle come out in the inputs. So, I want to go from -2 to -1. How do I change each input in order to get there? And again, backpropagation sounds pretty familiar, right? Well, let's take a closer look. Ooh, zoom in. Would you look at that? If we treat a neural network as a map from automatic differentiation and we perform reverse mode differentiation, what do we get? Backpropagation. Well, we get we have to do a couple more things and then we get backpropagation. But in fact, backpropagation is just a subset of what is possible with automatic differentiation. In fact, it is a, how do I say this? A special case of reverse mode automatic differentiation. Because what do you do when you do backpropagation? You change the output layer a little bit. You say, okay, I want to go here. I want to go down a little bit. I want to minimize this function slightly more. What happens if I do that? How do I change the weights along each edge when I'm going back towards the intermediate layers, the hidden layers? Okay, maybe this layer needs to change a little bit up. Maybe this layer needs to be slightly weaker. You're just doing reverse mode differentiation. All you've done, you've taken the network, you've put it in a map, you've put it in a tree, and you've differentiated backwards along the tree to see which inputs can affect your output. And I think that's beautiful. Now, when it comes to implementation of automatic differentiation, it's kind of hard to describe reverse mode. When you think of just this sub-problem of neural networks and backpropagation, there are so many libraries and so many different sort of Python, Julia, R, other programming languages that I've never used before. There's tons of different things. TensorFlow. All of these things, all just trying to do some backpropagation. So I don't think I'm going to have time to explain how reverse mode works, and I don't think I could. It's really complicated. Well, the implementation of it is, at least. But forward mode is actually quite simple to explain. Ooh. So what you can do to implement forward mode is you can actually just take the function, write out the source code, boop, 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 boop. And when you're doing this tree sort of stuff, when you imagine the tree that we're doing, we sort of boo boo boo, write some things, a fantastic tree. All you have to do is you can teach the computer how to edit your source code that you in fact get the derivative when you run the function. That's one way of doing it. Another way of doing it is with operator overloading. If you know more about that, just Google forward mode differentiation operator overloading. It's kind of incredible, the maths behind it. In fact, this is an introduction, and hopefully it's given you some sort of taste of why automatic differentiation is so beautiful. There's also a bunch of other things that I wish I could mention if I had time and if I understood them properly enough. But I really hope you've enjoyed what you've heard. And if you haven't, that's a shame. I made you sit through all of it, didn't I? Well, thank you very much for listening. Thank you very much for watching. And thank you very much for coming to the Warwick Data Science student-led speeches, talks.